Okay, I'm going to take you through this number 6 on the PhET activity, the projectile motion PhET. So it says challenge time. We want to find an angle first, and then we'll find a velocity that will cause us to hit the target. So make sure to turn air resistance off, raise the cannon to a certain height, blah, blah, blah. So the height that I'm going to pick is 10 meters. Now, because it's 10-meter height, I know my initial position in the y direction will be 10 meters. My final position in the y direction will be 0, and therefore our delta y, or change in position in the y direction, will be a -10 because it's going down 10 meters. And then it says we want to set the initial speed to 18 meters per second. So this is like the hypotenuse of our triangle, all right? That's the magnitude of the velocity, and that's the total velocity, so not split up into x and y components yet. Now it says move the target away 20 meters from the cannon. That's going to be our range, or our delta x, our change in x position. And then it says using kinematic equations in your brain, determine a way to find the angle that will cause your projectile launcher to hit the target. Now I give you a hint here. The initial velocity vectors x and y components can be written by v initial sine theta and v initial cosine theta respectively. This will make it possible to solve algebraically for theta. Don't use guess and check. So we're going to actually find an equation in which we solve for that theta with all of these things. So again, I chose 10 meters as the height to set my cannon. You can choose whatever you want. I actually want you to choose something different than what I chose so that you can actually try this problem by yourself, okay? Now, first and foremost, because we know that our initial velocity is that hypotenuse, we have to find equations for our x and y components. Now, I did give them to you in the prompt for this problem. So again, the initial velocity in the y direction is equal to v initial times the sine of the angle. And then velocity in the x direction is equal to v initial times the cosine of the angle. Remember, I just put velocity in the x direction because in the x direction, velocity doesn't change because we have no acceleration in the x direction in projectile motion. It's only in the y direction. Now, the next thing I want to do is I want to find an equation for time. The reason for this is because this is how we relate the x and y directions, remember, is with time. So the way I'm going to do this is I'm going to use the only equation we use in the x direction, which is vx equals our range, delta x, divided by time. If I solve this equation for time, I get time is equal to our range divided by the x velocity. So I do know an equation for x velocity, and I do know what the range is. I'm not going to plug in range yet for this. I'm going to actually wait until later when I have everything written down in equation form. So I'm just going to leave delta x as it is because I know what it is. And then I'm going to plug in for vx, v initial times the cosine of the angle. Okay, so now I have an equation for time that I can use to then plug into my equations in the y direction. So now what I want here is I want an equation that has time in it, that has my delta y, my change in position in the y direction, that has my initial velocity in the y direction, and that has acceleration, because of course I know that the acceleration in the y direction is equal to a negative 9.8 meters per second squared. So the equation I want is the second basic equation, delta y is equal to initial velocity in the y direction times time plus 1/2 acceleration times time squared. And so what I want to do with this equation now is I want to plug in my equation for the velocity initial in the y direction and the equation for time that I just solved for. Okay, so I have my delta y is equal to initial velocity in the y direction, which is that initial velocity times the sine of the angle, times time, which was delta x, divided by v initial times the cosine of the angle, plus 1/2 times acceleration times time, delta x, divided by v initial cosine of the angle, squared. Now, a couple things here. The first thing I'm going to do is I'm going to expand that squared term. So basically, since it's a fraction, I'm going to square both top and bottom. Since I have on the denominator the v initial times the cosine of theta, it will be v initial squared and times cosine squared theta. So if I do that, I get this. Okay, so another thing I want to do is I want to, number one, cancel out this V initial with this V initial, because since those two things are being multiplied together, we have a V initial on the top and a V initial on the bottom. That cancels out. Another thing I want to do is I'm actually going to take out that cosine squared theta on the very last term. I'm going to separate that out from the other stuff. So let me do that really fast. This is a lot of steps, I know, but bear with me. Now, the reason that I did this is we now want to use our trig identities to help us solve this problem. So what I mean by that is trig identities, and we can see them, I pulled them up here somewhere. Thought I had them. Oh, here they are. My trig identities here. Now, I know that one thing I have over here, you can see, is I have the sine of the angle divided by the cosine of the angle here. So using trig identities, I know that sine divided by cosine right here is equal to tangent theta. So because of that, I can then plug that in. I meant to. So tangent of theta is equal to sine theta divided by cosine theta. So because of that, I can then plug that in for this right here. So I get delta y is equal to delta x times the tangent of theta, okay, plus 1/2 a times that delta x squared over v initial squared. And then this whole thing, this 1 over cosine squared, I also want to use a trig identity for that. I end up getting 1 over cosine is just the secant, right? Do you see this right here? So secant theta is equal to 1 over cosine theta. Also, and I'm going to write that down, 1 over cosine theta is equal to secant theta. So because of that, I can use 1 over cosine squared theta is equal to secant squared theta. And another trig identity is that secant squared theta right here is equal to 1 plus tangent squared theta. All right, so I also want to use this one right here. So I end up getting that this is equal to tangent squared theta plus 1. So now what I'm going to do is I'm going to plug this right here in for that right here. Okay, so now it's multiplied by tangent squared theta plus 1. And then now we're getting somewhere, okay? Now what I'm going to do here is I'm actually going to start plugging in the numbers for all of the other stuff that I know. So I know delta y, because I'm using a height of 10, is a negative 10 meters. Delta x is that 20 meters times the tangent of theta. And then I'm actually going to be subtracting 1/2, well, adding 1/2 times negative 9.8. That's why I said subtracting. And then delta x is 20, so 20 squared over initial velocity was 18 squared, and then times tangent squared theta plus 1. So I'm going to solve all of this stuff first. So we get 20 squared divided by 18 squared is 1.234. And then I'm going to multiply that by negative 9.8 and multiply that by 0.5 or 1/2. We end up getting a negative 6.05. All right, and then I have times the tangent squared theta plus 1, and then negative 10 equals 20 tangent theta. So now what I have to do here is I have to distribute this term to both this and this right here. So we get negative 10 equals 20 tangent theta minus 6.05 tangent squared theta minus 6.05. That's a negative, and I'm distributing that negative. Now, what we need to do is we need to put this into the quadratic formula. Well, first I'm going to solve it so that it looks like it's the quadratic formula. So we get 6.05 times tangent squared theta minus 20 tangent theta, and then I'm negative 10 plus 6.05. We end up getting a negative 3.95, and that's all equal to 0. So here what we're going to do is we're kind of just going to substitute x in for tangent. So meaning this is like the quadratic formula having 6.05x squared plus 20x minus 3.95. Okay, so my x here is equal to tangent theta. Okay, so what we end up getting is 6.05x squared minus 20x minus 3.95 equals 0. And then I'm just going to use the quadratic formula. So we get x equals negative b plus or minus square root of b squared minus 4ac. All over 2a. 2 times 6.05. Okay, so under the square root, I get 20 squared, and then we're going to add 4 times 6.05 times 3.95, and then take the square root of that. I end up getting x is equal to 20 plus or minus 22.26 divided by 2 times 6.05, which is 12.1. All right, so x ends up being either 20 plus 22.26 and then divided by 12.1, 3.49, or x equals 20 minus 22.26 divided by 12.1, or a negative, negative 0.187. All right, so remember, x is equal to tangent theta. So now what we need to do to get theta, we have to take the inverse tangent. Okay, so tangent to the negative 1 of that x was 3.49. We end up getting a 74 degrees for that one. And then we get an x equal, or sorry, if we do the other one as well, we get angle equals tangent negative 1 of negative 0.187. And so for that angle, we get a negative 10.2. Okay, and I'll show you what these mean. Now, first and foremost, and this is degrees. Oops. First and foremost, let me put my thing up to 10 meters here, my cannon, and then this is at 20 meters here. Now I want the speed to be 18, and then I know that I got two answers here. I got 74 and I got negative 10.2. Now 74 degrees, if I put it up to 74, this should work. So let's see if it works. Cross your fingers. Yeah, bullseye, look at that. So it worked out, right? And then negative 10.2, I won't be able to do points on here, but I hopefully will be able to get down to negative 10. We'll try that. Negative 10 is right there. So you can see it should be negative 10.2, so it'll be a little bit lower. So if I was able to get to negative 10.2, then I would actually be able to hit that bullseye down there. But it's a little bit past it because it's a little bit above that negative 10.2. So you can see that I did get two answers here, but the reason I got two answers was because you either have a positive angle or a negative angle at which you can actually hit this bullseye.